All right, so in the last few lectures, we studied SO3 and SU2, the group of special orthogonal matrices that transform the basis of a vector space of 3 dimensions, a real vector space of 3 dimensions, and these special unitary matrices that transform vector spaces, complex vector spaces of 2 dimensions. These guys preserve metrics. They preserve metrics because this preserves the sesquilinear symmetric metric. This guy preserved a bilinear symmetric metric. So that's what defined these guys. And this guy with the S means it has modulus unity, and this guy has modulus unity. The determinant has modulus unity. That's what the S is for. So we did that analysis, and we discovered that both of them ended up with Lie algebras. These are the Lie groups, the matrix Lie groups. But we both recognized that for both of them, they had the same Lie algebra. We call this script or Gothic SU2, Gothic SO3, but they were both 3-dimensional, and we were able to write their basis vectors as x1, x2, and x3, and we were able to find a basis for this guy where they both had the same structure constants, and therefore their algebras were the same. Okay, so this is kind of famous, right? The relationship between SO3 and SU2 is famous. If you studied quantum mechanics, you've learned the connection between these two, or tried to. They don't really necessarily spend a lot of time on it, and it's kind of complicated. It's not presented very well, and through studying these things through physics is always going to be a problem, because we want to spend time talking about physics, not necessarily mathematical models in deep detail. That's the point of my lectures, by the way, is to sort of clear that up to the extent that I'm capable of clearing it up. But so this is famous connection. But Gilmore says, when you really look at the math of this, there's actually another guy out there, the special linear group acting on one-dimensional geometric spaces of the quaternions. And that guy is also related to SO3 and SU2 by the fact that it too shares the same Lie algebra. And so that's what we're going to demonstrate today. We're going to demonstrate that this guy out here is also a member of this sort of family of groups that share the same Lie algebra. And we're kind of gearing up to prepare for the question of how do you get from the Lie algebra into these groups? What's the relationship between these groups that they share the Lie algebra? Every group has a Lie algebra, but one Lie algebra may have several groups associated with it. That's an important question to understand. So we're going to get to that. So now, but understanding what we're dealing with here is this is ultimately we're dealing with the geometric space is a geometric space of one dimension, and therefore its basis vector is inevitably going to be a column vector with the number 1 in it. But it's one-dimensional vector space of quaternions, so its scalars are always quaternions. And so we can look at it as though it is a 1-by-1 quaternionic matrix, which we will, for the underlying vector space. This, by definition, is the set of 1-by-1 quaternionic matrices, right? So we're going to keep that in mind. The fact that this is 1-by-1, you think that would make it really simple, but it's actually a little confusing because there's a tendency to want to turn the whole problem into simply quaternionic mathematics, meaning if I took this member of SL1Q and I operated it on the basis of the underlying geometric space, or say I choose a basis of the underlying geometric space to be, some arbitrary member of the space. It's one-dimensional, so I can pick any quaternion R times this basis, this unit sort of basis vector, which I'll just draw as a column vector with a 1, and ultimately QR ends up being the new basis. Well, why do I need these? Why do I need to keep around the matrix notation? Why don't I just treat everything as though it's quaternionic multiplication? So you could, because the two processes for a 1-by-1 matrix are the same. But we're going to sort of try to stick as we can with forcing this to be a matrix, and even though it's one by one, I'm going to talk about it as though it's a matrix. So we'll write an arbitrary quaternion in this form. There's this real part, and then there's this complex part, but we have now three complex numbers, I, J, and K. And this whole thing obeys its own multiplication rules, which I'll just write down. And this is the multiplication table. Gilmore, by the way, instead of I, J, K, he uses lambda 0, lambda 1, lambda 2, and lambda 3. I just get tired of the subscripting, so I'm not going to do that. But in the book, it's a different notation. But this is our multiplication table that drives quaternionic mathematics. So we have these three complex numbers, and I guess I don't think there's any simpler way to do this. I mean, obviously, each of the complex numbers squared is -1 on their own. The problem is, of course, multiplying them together. I times j is k, but j times I is minus k. So you get this anti-commutativity built in. All right, so we do know that if we're going to, say, transform a member of the underlying vector space, and we'll call that member, say, the vector R, or the basis R. Say our underlying vector space has a basis R, and we transform that using a member of SL1Q. So remember, this guy is SL1Q, and this guy is the underlying vector space we would call V, right? But they're the same object in this particular case, right? Because V is a vector space over the quaternions. This is a matrix space that happens to be it's a one-dimensional object. If this was a two-dimensional vector space, you'd have RS, and this guy would be a 2 by 2 dimensional matrix, which would look very different. But one by one, they converge into mathematically the same object. So this guy would be Q. Now clearly the identity for SL1Q is going to simply be the number 1 here, right? Where we have Q equals 1 plus 0i plus 0j plus 0k, which is equivalent to a complex number, a plus ib, but b is 0, right? So since an arbitrary element is written as q and the identity is written as 1, an arbitrary element close to the identity is always going to be 1 plus some small quaternion, q. And the way Gilmore likes to represent a small quantity is he puts his little delta in front of it. So this means a small quaternion. Well, what's a small quaternion? Well, a small quaternion is each of these coefficients in front of all the complex part and in front of the real part are just tiny compared to 1. And what this inevitably means in a strict mathematical sense is when it's small, you can only preserve linear pieces of things, and you're allowed to throw away quadratic or second order pieces of things. All right, so what do we mean by a small quaternion? Well, a quaternion that's close to the identity. The identity is just the unit quaternion with no complex part and 1 for the real part. So if I take that and I add a small quaternion to it, what I'm doing is I'm taking the quaternion 1 and I'm adding a small real piece to it, a small I piece to it, a small j piece to it, and a small k piece to it. And this is just a quaternion. Now remember, I'm trying to think of this as a matrix, right? So this is the matrix, the 1 by 1 matrix of a quaternion close to the identity. This is the matrix of a quaternion close to the identity. Now, I can do, in the context of this sort of absurd matrix look at it, I can consider this to be the sum of 1, 2, 3, 4, 5 different matrices, like this, right? This guy here is this matrix, this guy here is this matrix, and then these three, I pull out the real part. Remember, this is just a little real piece, and I just keep the complex parts behind. So I have now 4 matrices here, but these two are 2 real numbers, right? So I can gather them together in sort of a single real matrix, 1 plus delta Q0. And the rest I'm going to write like this, delta Qi lambda I. So remember how I wanted, ijk, I'm so smart, I'm going to use ijk. I'm going to use ijk instead of, Gilmore's tediously subscripted lambda 0, lambda 1, lambda 2, and lambda 3. So I outsmarted myself because now I want to use the Einstein summation convention, but ijk is not amenable to that, so I got to go to his lambda I. So understand that this is lambda 1, lambda 2, and lambda 3. And they're actually matrices, right? I want to think of lambda I, lambda 1 is the matrix that contains the single 1 by 1 quaternion I. Okay, so I've got this down. And the other place where I just outsmarted myself is by combining these two together. I lose the fact that there's actually 4 basis vectors in the algebra. Remember, the nature of the algebra is it's that infinitesimal part that when added to the unit of the group gives me a member of the group that's infinitesimally close to the unit. So what I really want to do is I want to keep that separate so I can write it as delta Q0 times basically the unit quaternion as understood as a matrix. And because of this now, I can identify all of this with a member of the Lie algebra, a very small member of the Lie algebra, and thereby I can break down the basis vectors of the Lie algebra, which will be 1, the matrix 1, the matrix lambda 1, the matrix lambda 2, and the matrix lambda 3, where I guess I really should put this sort of in the I got to decide, do I want lambda 1 to mean the matrix that contains I, which is what I've been saying, or do I want to write the matrix lambda 1 where lambda 1 equals I, right? And I'm positive that I'm going to get that confused a lot. I want to focus on everything being a matrix, though, so I kind of like this notation. I'll probably slip in and out of it, but you've got to be to get this stuff straight, you just got to know it really doesn't matter. Okay, but we are in a position now to write down the Lie algebra, right? So the Lie algebra, which will be script S, script L, 1, Q, is going to have 4 elements to it. Lambda 0, lambda 1, lambda 2, and lambda 3. Where now I'm writing them as lambda, but I'm committing to this. Lambda 1 is essentially this, all right? And etc. Lambda 2 is a matrix J. So now you're going to think of lambda 1, and that's fine. The way we did with generators before is I wrote xi, and that, of course, was in a place of a matrix. So this is fine. So we're going to go with, these are the 4 elements, or the 4 basis vectors of the vector space SL1Q. And, of course, embedded in that is our natural commutator, which is the bracket operation. And what do we have left to do? Well, we've got to figure out the structure constants of the algebra. So our next step is to take these guys here, which we've determined as our basis, and we're going to look for the structure constants. Now, this portion of the lecture, I'm actually sort of redoing something, but you'll notice that the special linear group, we have not yet imposed the constraint. We have not yet imposed the constraint that the modulus has to be unity. So what we've actually done is we've found an element of the general linear group. I guess I should write this as script G, because we've got this lambda 0 here. Later on, I will remember to fix this, and this guy goes away altogether, and we are left with a 3-dimensional vector space for this special linear group. But as far as, so we've basically calculated an arbitrary element close to the identity, which is the general linear group. We have not imposed the constraint, but I'll do that in a few minutes. Well, the first thing we understand is that the bracket so we're looking for the bracket operations of the basis matrices, and where I'm going to this is now the bracket operation, right? This is now the groups, the algebraic product, right, in the Lie algebra of two members of the Lie algebra. So now I'm not writing the members of the Lie algebra as a one-by-one matrix. I guess I could, right? You could say, we have a one-by-one matrix like that and a one-by-one matrix like that, and this is the matrix product of these one-by-one objects, right? I mean, to really, really drive home that this is a matrix algebra, everything has to be a matrix. But with a one-by-one, it's just seems like such a waste of effort. So Gilmore and probably every other reasonable person in the world just says, all right, we're dealing with just these quaternion, because there's a complete isomorphism between the straight-up quaternion mathematics and the mathematics of one-by-one quaternionic matrices. So we don't even bother, and just don't confuse these brackets with some sort of matrix brackets. This is the group multiplication operation, which we know is defined this way. Regardless, lambda 0 is the real unit or the real identity. So this commutes. So it commutes with everything. It commutes with lambda 1, 2, and 3. So this difference is always 0. And that immediately tells us that every structure constant that has a 0 down here is going to be 0. Okay, so that gets us a long way. So let's look at the other ones. Okay, I hope I got this right, but lambda 1, lambda 2, the bracket operation on those is 1, 2 minus 2, 1, which I just wrote as ij minus ji. This is sort of the way I think about the math. ijk is easy for me to remember. So that product is k. Well, you switch it, you get minus k, minus k, so you get 2k. Right? So we're going to do this so what this tells us is that C312 equals 2, right? That's what this coefficient here is. The 1 and the 2 come from here and here. This 3 represents what actually ends up over here, which is just a k. But we notice that there's no I, j, or real part. So these guys must all be 0, and their negatives must be 0 too. So the 2, 1, the 2, 1, and the 2, 1, those guys are also 0. So we're zeroing in on that. Now we just got to do the rest of them. And I'll just write them out pretty quickly. So here it is for C13, and that leaves us with C23 to do. Oops, C23 is next. All right, so this is what we end up with. I didn't even put all the rest of the ones of the zeros. These are the only non-zero ones, right? This guy and his opposite, where opposite means we're anti-symmetric in these lower two indices because this guy is obviously anti-symmetric in those indices. And the definition, I guess I should write down a reminder of the definition, but it goes lambda I, lambda j equals C I j summed over k lambda k. Right? As a reminder, right, this has to be a member of the algebra. Therefore, it's writable in a basis. It can be a basis decomposition. This is the basis decomposition of the product of two basis vectors. So it has to be summed over the basis. Turns out this sum, everything is 0 except for one term, and that's the term that's missing on the left-hand side. Okay, so this is the Lie algebra. So we figured out the Lie algebra, but we don't like this Lie algebra. We don't like it the way it's written here. We want it to be cleaner. We don't like 2's, for example. So what we actually do is we change our basis a little bit in order to clean up the Lie algebra. Because remember, it's just a basis, right? Where did I write that basis down? This is just, this here, this is just a basis that we chose. We kind of zeroed in on the identity and we made some logical calculations and we said, oh, okay, lambda 1, lambda 2, and 3, those are the basis vectors. They're multiplied by components. They must be the basis. But what we can do is I can take any factor of those or any scalar. I can multiply any of these basis vectors by a scalar inside the algebra, which in this case is a quaternion in the algebra, and I can change the basis, right, arbitrarily. So I'm going to do that. I'm going to change it so that everything looks like the basis vectors are now going to go to. The arbitrary change I'm going to make is the basis vectors will be, let's see, how do I want to write it down? I want to go to this basis. This basis here. The basis will be the quaternion, the 1 by 1 quaternionic matrices xi will be minus 1/2 times those 1 by 1 quaternionic matrices lambda I, right? So how would that affect things based on this calculation? Where did I go to this here? Well, first of all, it doesn't affect this at all, right? If I go minus 1/2 here and minus 1/2 there, right, what happens? Well, I end up with a minus 1/4 out in front, and that's still going to be 0. So it doesn't change these guys at all. So what happens if I do that here? I got a minus 1/2 here and a minus 1/2 here, which would make this now x1, x2, right? That's what we're interested in, right? So this gives me a 1/4 here. I guess this would be just a plus 1/4, not a minus 1/4. This gives me a 1/4 here out in front of this, and that gives me a 1/4 there, and that goes over to here, so that's over 4, so this is over 4, so I get 1/2 k, which is minus x3, right? Because x3 would be minus 1/2 k by the definition, right? By this definition, but we have positive 1/2 k, so we have minus x3. So that means the coefficient is actually minus 1 in the new basis. So this minus 2, this 2 here becomes a minus 1, and these guys are still 0. And that basically happens everywhere, right? Everywhere you see a 2, you replace it. Everywhere you see a, we got to change the sign and turns the 2 into 1. So this will be a plus 1, and this will be a minus 1. And now, because we've done that, we have our ultimately in this basis xi xj equals minus epsilon I j k x k, which of course is the exact same commutation rules we used when we did SU2 and SU3, which is why we're changing this basis. We're changing this basis so you can really see that the algebra is the same. And so we're now in a basis where the algebra is truly numerically identical to the other algebras. Otherwise, you're kind of concealing this fact. But understand the choice, and this shows up a lot in physics. You say, oh, we're going to take these basis vectors to be minus 1/2 of that. And it's like, well, what the heck are you doing that for? And it's all a matter of convention. We want the commutation relations to look like this. In other words, we want ckij to equal minus epsilon I j k. Well, no, I don't need the xk there because I'm just identifying the coefficients. Let me just make sure this is all right. So this guy here, it's 1, 2, and the result is 3. So 1, 2, 3, this would normally be 1, but it's a minus 1, and we come in with a minus 1. 2, let's do 1, 3, 2, we got a plus 1. So what would this be? 1, 3, 2 is one swap, right? 1, 3, 2 is actually 1, 2, 3 with one exchange, so it's definitely an odd exchange. So the epsilon there gives us a minus 1, but we have a minus 1 in front, so we get a positive 1, and that's what that is here. Okay, so this is correct. All right, so now we have our Lie algebra. And I'm just going to write it down this way. The Lie algebra has 4 basis vectors, and we've identified its structure constant. So we know everything we need to know about the Lie algebra because the structure constants tell us about the bracket operations. So we can take the bracket of any 2 vectors inside the Lie algebra. And so we're done with that. And then, of course, we still have the group. And you remember I've now gotten into the habit of writing the group as this blue box with the coordinates already written on it because we understand the group is a manifold. There's an identity element, and then there's the neighborhood of the identity element. So any element of this group is a 1 by 1 quaternion The identity element is the 1 by 1 quaternion surrounding just the real valued quaternion. That's this element right here. And it's a 4-parameter group. It's a 4-dimensional as a Riemann or as a manifold. It's in R4, right? Because you've got Q0, Q1, Q2, and Q3. Those are the components of the quaternion that locate each of these 1 by 1 matrices in this space. And we have our mapping that goes from the Lie algebra to the vicinity identity, which is going to be the identity quaternion plus a small member of the Lie algebra, or equivalently, any member of the Lie algebra multiplied by a small number. So there's our M, and now M is just an element of well, I guess I should do it. M is a matrix, right? So this isn't, I've got like the matrix of a matrix in there, right? So epsilon M, and M is an element of the special linear group 1Q, and epsilon is really small, so it's going to force M to be small. That's one approach. The other approach was to say 1 plus M, where we understand that M is close to the 0 of the group, right? It's close to the additive identity of this algebra, of the Lie algebra. So we either say M is a small matrix in the Lie algebra, or we say M is any matrix in the Lie algebra multiplied by a very small number. We're going to use this approach more and more, so why don't we just stick with that? Oops, wait a second. I've made a gross error here. Well, not yet, I guess. I've identified this as the Lie algebra of this, which is wrong because this guy doesn't belong in there. What have I forgotten to do? What did I forget to do here? I forgot to impose the constraint. Remember, this is all members of the general linear group of 1 and Q. What I've basically done is this right now, as it stands, this is the general linear group of 1Q. I can make any one-dimensional quaternionic matrix with this basis, right? I haven't imposed the constraint that the determinant of these guys have to have, the modulus of everything in here has to be unity, right? And that's this determinant constraint. So if I took a random element of GL1Q, right, I'll call it, say, Q, I want only those guys whose determinant, right, or the modulus of the determinant, I guess, is unity. And that's a constraint on these 4 numbers, right? If I take arbitrary 4 Qs, this isn't going to be true. I got to zero in on just the ones where this is true. So the modulus of 2 complex numbers, or 2 quaternions, is going to be it's a general quaternion's conjugate times Q, where the conjugate of a quaternion is the same thing. All of I goes to minus I, J goes to minus J, and K goes to minus K, but the real part doesn't change sign. So an infinitesimally a small quaternion, 1 plus, say, delta Q, its modulus times 1 minus, times, not minus, 1 plus delta Q, right? What is that going to equal? So the modulus, I'm using these Q's, these little Q's, I'm using superscripts here. For some reason I use subscripts up here, but remember, we want the sums to work over these generators, so I have superscripts. But this infinitesimal piece, the product of this is going to be blown up like this, where we're singling out the real part, and then we take the opposite in sign due to this conjugation of the complex part, and we leave the sign of the complex part alone here. But if you look at this, what's going to happen is this first term is going to just come straight out. So if you blow this up, you end up with, if you blow up this product, right? Well, first of all, I took this and I separated to its real and complex part, took the conjugate to get this negative sign. So what ends up happening? Well, let's see. This is a higher order term. This Q0 commutes with everything, but this is not only a higher order term, but it also cancels directly. That's a higher order term. This linear term cancels with that linear term, and you're just left with 1. Ultimately, you're left with 1 plus 2 delta Q0. So that basically means this modulus has no hope of being 1 unless the Q0 part is 0, right? And so that's the point, is that if you go back to the algebra that we're dealing with, this algebra here, right, the Q0 term is always 0. So an arbitrary element of this algebra is a Q0 plus a Q1 plus a Q2 plus a Q3, right? So it's Q0, Q1, Q2, or Q2, Q3, but this guy always is 0. So the actual Lie algebra for the special linear group is only 3-dimensional. It's only 3-dimensional. So there's only 3 parameters. I was saying there was 4 earlier. That's completely wrong, right? So this guy's gone. And now this general linear group, I can now either promote it or demote it, depending on how you look at things. It's now the special linear group. It's either promoted if you think that's a special thing, or it's demoted if you think the size has gone down. But anyway, so now we're back in business, right? So the structure constants, it still works out that these structure constants are the same as SU2 and SU3. When I was saying that this is the same as SU2 and SU3, remember, I was forgetting this part, right? SU2 and SU3 doesn't have this part because there is no 0, right? There's no 0 term. So all that goes away. So these structure constants here are in fact the same, and now there's no 0 piece, there's no 0 subscript for the structure constants. It's just these. Okay, so now we're back in business. So now we can work on this exponentiation. So the exponentiation, we all understand how to do that. When I write the exponent of a matrix, I think this power series. Now I'm using my 3 parameters are now theta, just to stick with Gilmore. So that's theta 1, theta 2, and theta 3. But they're finite parameters now, right? That's the beauty of this. We're looking for a finite group element. So this is what I'm after. I'm going to blow this up a little bit. And the way we work this is, the clever trick here is we notice how does theta ixi squared look. We're going to be able to maybe cast out squares like we casted out cubes in our last lecture. There's always something clever here. There's always something clever. In this case, the cleverness is going to be based on a calculation of theta ixi squared, and we'll have a look at how that affects these even powers. So just to drive it to death, this guy really means this squared. If you blow up the sum, when you square this, each term will come in with its own square, and then there'll be all these cross terms. And the cross terms, we have to be careful because x1, x2, and x3, they don't commute. Although theta 1, theta 2, and theta 3, the parameters, those are real numbers, right? Remember, this is a real manifold, so everything's real as far as those parameters go. So those guys commute, although I've been a little disciplined down here. So theta 1, theta 2 equals the same thing as theta 2, theta 1. But x1, x2 does not equal the same thing as x2, x1. But the fact is x2, x1 is the opposite, or x1, x2 is the opposite of x2, x1. So all of these terms actually cancel, right? These terms actually cancel. This is because, let me get this right here. The anti-commutator, you can calculate this for yourself. We used this in a previous lecture. So the anti-commutator, well, let's see, xi, xj equals 0, right? Which means xi, xj equals minus xj, xi. And the anti-commutator is xi, xj plus xj, xi equals 0. Anyway, the bottom line is all these guys cancel. Oops, red. All these guys cancel. And what you're left with is this. So now we're left to evaluate that. Well, x1 is minus 1/2 lambda 1. So x1 squared is 1/4 of lambda 1 squared, which is minus 1, which is minus 1/4. And by the way, that's going to be true for all of them, right? It's going to be true because this is good for x2, lambda 2, x3, and lambda 3. It's the same expression. So all of these guys are minus 1/4. So I can finally write, it like this. These 3 squared times, now this is going to just be a real number. So we'll define that to be theta squared without a subscript. That's going to be the sum of the squares of the 3 parameters. So it's minus theta squared over 4, and we recognize that as minus lambda 0. I'm now putting it in Gilmore's form, 1/2 squared theta squared, for what it's worth. Gilmore likes to write it like this, where lambda 0, of course, is just the real number 1. And we've seen this guy, theta, pop up in all 3 of our analyses so far. And so we define, I guess I should write down, theta squared is defined as the sum of those squares, where I'm dealing with this exponentiation of a number with a superscript index. So I have to throw in these parentheses. So now we're going to do the usual thing. We take this, we're going to break it up into the even terms and the odd terms, and clearly we have some insight into what these even terms are going to look like. They're going to be the nth power of our substitution for the square there, and likewise we'll be able to address this. So just addressing the even terms, let me pop that out down here. We'll put it right here. I'll shrink it a little bit. Okay, so let's study just the even terms. I guess the first thing I'll do is I'll remind myself what the square of this is. The square of this is minus the unit identity, 1/2 squared theta squared. So I'll do the first, is the obvious thing, is this guy here. I just blow up into the square to the n, and obviously I'm going to substitute for this real number expression. In that substitution, this -1 that would be here becomes -1 to the n, because I raise it to the nth power. The -1 will land inside here. So that's what that is. Then this guy ends up being theta squared. So it's theta squared to the n. So it's theta to the 2n. And then I have this 1/2 to the 2n right here. And that brings us to the final step, where I just sort of simplify these things and make it look like the cosine series, right? So cosine series is even. So n equals 0, you get 1s, and ends up with being cosine of what's being raised to this 2n power. So it's cosine of theta over 2. Remember, theta is the sum of the squares of the individual parameters. So that takes care of the even terms. Now the odd terms will be taking this one and moving it down here. Well, let me just do that. So I'll shrink this guy down. And now we'll just break this guy down the same way. So the first step is just to take this guy apart a little bit, so we see the part we can substitute for and the spare part here. Obviously the spare part doesn't depend on n, so that's going to immediately come out in front. So the direct substitution, pulling this guy out in front, leaving this guy behind, and we have the usual problem, right? The exponent doesn't quite work, and we have this -1. So I can clean that up without much trouble by turning this into a -1 to the n, where I'll make my changes in black. So that gets rid of that -1. And then what I have to do is I need another factor of theta here to make this +1, right? So I need to divide this guy by theta, and the problem with that is it ends up giving me a Oops, I'm sorry. I need to do an extra factor of theta over 2, so I need a 2 here. And when I do that, this guy then is the sine series. So I end up with 2 times theta hat I xi, because theta divided by theta we call theta hat, and that equals that, and then I have sine theta over 2. Right now, when Gilmore does this, he ends up he immediately goes with he takes 2xi and he writes that as 2 times minus 1/2 lambda I, which equals minus lambda I. So this ends up being in his notation, which I'll do in red here, is going to be it's going to be theta hat I lambda I minus theta hat I lambda I sine theta over 2. That's how he ends up with his final version. So the bottom line is, now we go back to this whole point, right? Remember, this guy here was exp of m equaled that, right? In other words, we're working to find the general matrix of SL1Q is this guy. Well, we've just figured out what it is. And I will write it down fresh here. And so this is the, so if we rewrite, we're looking for the general exponential of a matrix from the algebra, which is ultimately this. This is the matrix from the algebra. That is what M is. And in the terms we've just done it, it's cosine theta over 2, where theta is this sum of squares, 2 x hat I xi in the xi basis. So, but in Gilmore switches back to the old basis, and that makes sense, right? This just becomes ijk, which is easy to understand. And here we have minus 1/2 ijk, so we have to change the sign and multiply by 2. I like it because it's in terms of the basis of the Lie algebra, but when it comes down to what is the quaternion, this is the quaternion, right? This is the real part of a quaternion, and this is the complex part of a quaternion, and that's the different elements. So this, in his language, this would be minus hat 1 I sine theta over 2 minus hat theta 2 j sine theta over 2 minus hat 3 k sine theta over 2, right? So now you can really see, and this is the real part, cosine theta over 2. And this is a quaternion where Q0 is this number, Q1 is that times that, right? So it's sine theta over 2 theta 1 hat, right? That's what Q1 is. So it's that times I. This is Q1 times I, etc. Q2 times I is this times this, and there's J, and then there's this times this, and there's K. So the answer is a quaternion, right? Which is, of course, it's got to be a 1-by-1 quaternion matrix. So there's the exponentiation. So I think that takes care of everything we need to know. Oh, there is one other thing. And now I'll save the one other thing for later. We should talk about the Lie group for the general linear group, right? I want to explain what happened to this guy. What's up with x0, right? What if we throw x0 in there? What difference does that make? It's still Lie algebra, so there is a Lie group attached to it, and it's the general linear group for one-dimensional quaternions. And that happened also with the special unitary group. We threw away one of our basis vectors to get from the general to the special, or from the unitary group of two-dimensional complex over the two-dimensional complex matrices. So from the unitary to the, so in other words, from U to SU, we dropped x0. And here we also dropped x0. And it was at the same place, right? It was when we calculated the modulus, which was the constraint. This guy had two constraints because it's a metric preserving group, right? today we just did. Well, let's review what did we do today. So today we started with the special linear group 1Q, whose one-dimensional, quaternionic matrices with a modulus of unity, a determinant of unity. We discovered its Lie algebra, and we discovered that its Lie algebra was the same Lie algebras we found for SO3, the group, and SU2, the group. So this is very related, and we'll talk about that relationship for the next few lectures. We did our analysis very carefully, understanding that we're dealing with a one-by-one matrix of quaternions, which is a little confusing because that's simply multiplying quaternions times themselves. And then we did yet another example of this exponentiation, right? And we showed, in this case, it was actually somewhat easy, but we ended up with something that looked very similar to SU2, which is not a surprise because the SU2 is very related to this. But in the end, we ended up with a quaternion, right? So we ultimately have to think of the final result. Remember, this is a matrix that's an element of SL1Q, right? This is the exponentiation of an element of the Lie algebra SL1Q is a matrix in the matrix group XL1Q. So when we think of this final number, I really need to think of it as a one-by-one matrix with a quaternion, right? That is the way we want to think of it, because we're always really focusing on just the matrix groups. Okay, so in our next lecture, we'll tie up a few loose ends and start comparing these three groups together.